this. Okay, so this is module 4, I think, in Canvas for this course. And so module 4 deals with geometry and measurement. And it comes out of this chapter 8 now. It used to be chapter 9, but in a previous edition. But it's chapter 8 of Martin Gay, who wrote a pre-algebra book that they used to use. And we don't use anymore because it costs, I think, $150 to buy a copy. So we went to this online book, but it doesn't have a specific chapter in geometry. So as a substitute, I'm going to use the PowerPoint presentations that you can download from the Pearson website for this Martin Gay book. So the first section is section 8.1, and it's all about lines and angles. And some of this we covered when we did a little bit of when we worked with triangles a few weeks ago. And so I thought I would just go through some formal definition of what lines and angles are and a little bit of very background geometry. So one of the concepts that is central to geometry is a plane, and a plane is a flat surface that extends indefinitely in all directions, right? So if you think of a sheet of paper that is flat and goes out, you know, for infinity to all directions, that would be a plane. And we encountered them when we did graphing a couple of last week, where we had the Cartesian plane. And so the Cartesian plane is one example of a plane, and a plane can rotate all the way, you know, through 3 dimensions, and so you have plane intersecting planes. And but a plane is a flat surface. And so then they talk about the most basic concept of geometry is the idea of a point in space. And so point has no length, it has no width, it has no height. All it has is a location. And so when we draw a point, we represent it by a dot. And then typically we label points with letters. So here they've got this point A, right? Now a line is denoted by the area between 2 points. So we have the line segment AB is all the points that are between A and B. And between any 2 points on a line, there's an infinite number of other points. So there's an uncountably infinite number of points between points A and B. Now, a line, this line defined by AB would be extending out to infinity in both directions. So it would go to minus infinity and plus infinity, and a line segment is just this finite chunk of the line AB. So the line segment is finite, line AB is infinite, and then the ray AB goes in one direction to infinity, but it starts, and so it has a boundary on one side or the other and goes off to infinity. So you can have a ray going to the left side as well. Right. Now an angle is made up of 2 rays that share the same endpoint called a vertex. So here's the vertex, and we encountered these when we talked about triangles, and we talked about supplementary and complementary angles, and they'll be addressed here in just a minute. So we would call this angle here ABC, and you could also call it CBA, but by convention, B is the middle point, is always the vertex angle. So we wouldn't call this angle ACB, right? Because B is the vertex, so it lies in the middle. Or we could just call it B. Or we could also call it X. We could define this angle here in X. And we'll talk about how we define the measure of these angles and how we quantify what that is in just a second. So angles are measured in degrees, and there are 360 degrees in a full revolution of a circle. And by convention, we talk about this as measured counterclockwise around the circle. So this is positive 360 degrees all the way around. So a right angle here is 90 degrees. And I'll get some specific examples, right? You also will see sometimes people talk about negative angles where they measure the degrees clockwise, and that's just measuring the angle this way, but that would be a negative angle by our standard measurement. So here's a couple of examples of angles. This one is about 45 degrees. This one is about 260, where you can see it goes all the way around the circle. Right? So those are examples of angles and how they're measured. So we can classify angles into a couple of different categories. There's an acute angle, which is between 0 and 90 degrees. And so that's an acute angle, right? And then there's a right angle, which is exactly 90 degrees. And we talked about that in terms of right triangles. And then there are obtuse angles, which are 90 degrees to 180 degrees. And so this would be an obtuse angle. When an angle gets bigger than 180, a straight angle, I'm sorry, is exactly 180 degrees. So you can see that 180 degrees, this straight angle, is actually two rays that are joined in a center point, and that's actually just a line. So a straight angle is just another name for 180 for a line. And we don't have a special term for an angle that's greater than 180 degrees, because a lot of people will just say, well, if it's greater than 180 degrees, I'm going to turn around and see if that ray is going this way. They would turn it around and measure it as a negative angle less than 180 degrees, so that you would have a negative acute angle or a negative obtuse angle.
Okay.
Yeah, so it's just by convention. And then sometimes you'll see angular distance measured in something called radians. And what radians are is a different unit for angular measurement, and we haven't gotten to units yet, but we will. And in a radian, let's see if I can go back. Yeah, okay. For radians, instead of we talking about degrees, we talk about radians, and there are 2 pi radians in every circle. So this would be an angle. If we had this flat angle here, that would be pi radians, and if we go all around, that's 2 pi radians. And so a right angle in terms of radians would be pi over 2, where pi is the sort of like the circular constant, and it's approximately equal to 3.14159, whatever, 28, I think, or something, right? So pi is just a number, and 2 pi is the number of radians in a circle, and that falls out of geometry and I'm sorry, trigonometry. And so we don't need to go where that comes into, but sometimes you'll see, like on a scientific calculator, it'll have a button that'll say radians, and all radians are is a different way of measuring uh, angular measure. And so 2 times pi, which is 6.28 something or other, is the same as 360 degrees. Classifying angles. What's next? Okay, right. And so we talked about this in terms of triangles. We talked about complementary angles and supplementary angles. And so I think they've got, oh, they didn't have any examples, but we talked about that before. So we talk about 2 lines. If we have 2 lines that are in the same plane, there are 2 cases. They can be parallel, and meaning that they extend alongside each other out to infinity on both directions, and parallel lines never intersect. And then they have intersecting lines, right? And so intersecting 2 lines that intersect will intersect at one point only. And that has some interesting properties when you get to algebra, when we do beginning and intermediate algebra, that this point has a special meaning for these 2 lines. And so you'll see that again. But be aware of that if you have 2 lines, there's really 2 cases. Well, there's 3. They could be on top of each other. But they can either be parallel, in which case they never intersect, or they can intersect at one point only, right? So parallel, this is what parallel means. This is what intersecting means. And the symbol for parallel lines is this double vertical line, and that would mean parallel. Now, the other way they can, there's a special case of when they intersect is if they form right angles. And so these would be 2 lines that intersect at right angles, and those are called perpendicular. And with that, we use this little symbol here, this inverted T, and that means perpendicular, right? And so this gets used in carpentry a lot, and in machining and drafting, where you want to denote something that's going to be a right angle. like a lot of times you'll see in plans where they have walls and they make sure that they get these perpendicular. So you'll have this n perpendicular to m here.
Okay, okay.
And that's what that means. It just means right angle. Okay. Okay, so vertical angles, and this is a classic geometry thing. So when two lines intersect, it forms four angles, right? So you've got angle A, angle C, angle B, and angle D. And the interesting thing about two lines intersecting is that the measure of this angle A is the same as this measure of angle C. And the measure of angle D is equal to the measure of angle B, right? And that is a classic geometry proof that I'm not going to go through, but if you take geometry, they'll go through and they will prove that A is equal to C and D is equal to B. And it's a classic geometry proof that vertical angles are the same for two intersecting lines. And you can use this to prove all sorts of interesting facts about triangles. And in fact, the law of similar triangles we discussed a couple of weeks ago, where we looked at ratios of triangles falls out of these vertical angles. That, for example, you can imagine that if you had a line across here and a line across here straight across, you'd form two triangles, right? And they're different sizes, but yet this angle here for this little triangle is the same as this angle here for this little triangle. And what you'd be able to show is that the angles here and here are the same as the little angles here and here. And these two triangles are similar, and because of these vertical angles, you can then show that the lengths of these sides, the ratio of all these sides, is the same for those two triangles. And that's, again, a geometrical thing that we're not going to do in this class, but it's something that if you take geometry, you'll do. Okay, two angles that share a common side are called adjacent angles, right? So A and D are adjacent angles. A and B are adjacent angles. C and B are adjacent angles. And D and C are adjacent angles. And they've got that all written out here. And the thing about adjacent angles is that they are all complementary. Supplementary, that they sum to 180 degrees. And you could see that because, as I said, a flat angle of 180 degrees is just a line. So we've got a line here, so that the sum of these two angles between here has to give you back out the flat line. So this supplementary angle for adjacent angles is another unique property of these intersecting lines, right? So all of these are adjacent, these are adjacent, these are adjacent, and these are adjacent. And
Yeah, I remember that. I think I took a geometry class in high school.
did you? Okay, cool. Yeah. So some of this stuff is review, and we'll just go
Yeah.
through a couple of these. But and then so the next one is called a transversal line. And so suppose you have two parallel lines, and or a line that intersects two or more lines at a different point is called a transversal, right? And so so this line is a transverse line, and it has an intersection point there and there. And if two parallel lines are cut by a transversal, then the corresponding angles are equal and the measures of the alternate interior angles are equal. So you can say that what we've got here is we've got all these angles formed by this intersecting line, by this transversal line. We've got A, B, C, and D, and then we got E, F, G, and H. And what this theorem says is that A is the same as E, is the same as H, is the same as B. I'm sorry, D. Let me try that again. A is the same as E, is the same as H, is the same as D. And B is the same as C, is the same as F, is the same as G, right? So all of these angles here, these four angles, G, F, C, and B are the same, and A, D, E, and H are all the same. And again,
Yeah,
you
they
can,
kind of like coincide. Like
yeah,
A and
exactly.
E, B and H, C and G.
Yeah, right. And you could see that because if you let this line here, uh, get closer and closer to this line, you can see that in the limit, what happens is A and E really are the same, can be the same angle. See that? That if you let this line sort of
Yeah.
creep down, down, and down, and finally it gets on top of there. But there's a point where it's infinitesimally close, and E and H are really the same angle, right?
Yeah. And G and F as well.
Yeah, and G and F as well, right? So so B and F become the same angle, and A and E become the same angle. So it's the same thing, and that becomes a sort of a calculus mixed with geometry problem. All right. Corresponding angles say of equal measure, which they just talked about. So the measure of A is the same as the measure of E is the same as the measure of H is the measure of D, right? And so all four of those are the same. And alternate interior angles are on opposite sides of the transversal between the two parallel lines. So these are the opposite. Let's see. Let's make sure I get those right. Corresponding angles, right? Are A, E, C, and G. Okay. Alternate interior angles are angles on opposite sides of the transversal between the two parallel lines. Opposite sides of the transversal. So these must be these two and these two. These are the alternate interior angles. Or no, I'm sorry, these two are the alternate interior angles. And so for the alternate interior angles, C is the same as F, D is the same as E, right? All right, so that's the end of that one. And that's just a bunch of definitions. And what I will do is I will put that up on Canvas, and I might narrate it and put it up also as a narrated PowerPoint so that you can take a look at it. And I'm going to go through one more, and then we'll call that a day. And I don't have a whole lot of, I don't have problems written up for these yet because it seems like this stuff is,
Pretty
well,
straightforward.
it's
Well, yeah.
straightforward, but I'll get some problems written up and put into Canvas. And the next thing we're going to do is
If you don't
perimeter.
want to, you don't got to. It's fine.
No, I think because I
Yeah.
it it won't take you very long to do them. I'll make them only 10 problems, and so it shouldn't take very long to go through. And
Yeah. Perimeters actually when I took this class in high school, I really liked perimeters actually.
did you? Okay, cool. So we'll just flip through this, and so perimeter. This is going to be, yeah, the perimeter of a polygon is the distance around the polygon, which is the sum of the length of its sides. So the perimeter of a rectangle, right? So the perimeter of a rectangle is the length plus the width plus the length plus the width. And so length plus width plus width. So the perimeter is 2 times the length plus 2 times the width. And I think we've gone through this, 2 length plus 2 width, and that's the perimeter. Right? So the perimeter of a square, all 4 sides of the square are the same. And so it's going to add them together for us. I guess I didn't realize this was animated. So it's going to say it's S plus S. So 4 times the side. So perimeter equals 4 times S. So the perimeter is just sort of what we would call a degenerate case of a rectangle, right? So where
Yeah.
it's the same thing. Perimeter of a triangle is A plus B plus C, right? And so it's side A plus side B plus side C. That's the perimeter of a triangle. All right. Now, the circumference of a circle is a distance around a circle. And this is where this variable pi comes in.
Yeah, you just times the diameter times
Pi
pi.
times the diameter, yeah. So the circumference divided by the diameter. Okay, so for any circle, the circumference divided by the circumference divided by the diameter is always the same number. It's always the same ratio, and we call this number pi. And it's approximately equal to 22/7 or 3.14. And it's actually 3.1415928 something or other, right? So, and this is something that the ancient Greeks worked a lot on, that they recognized early on that there was this golden ratio that was the ratio of the diameter of the circle, and they didn't have calculus or calculators And so they actually had to go and try and measure the circumference and measure the radius, and then they would do the division. And so for a long time, it thought that pi was 3, because that was the limit to how accurately they could measure things. When they had pieces of string and they have it staked out on the ground, and they would think, well, if I could do that accurately, it would be exactly 3, not 3.1 or something.
Yeah.
So, but now we know it's 3.141, whatever it is. And actually pi is, remember we talked about irrational numbers, how they go on forever, never repeat, and never terminate. Well, pi is one of those numbers. So pi is an irrational number. And there's all sorts of things you can do. And for example, pi is sometimes used as a series of random digits because of its characteristic that if you calculate pi to an infinite number of places, you'll get a random series of digits. So that's pi, and that figured in our. So the circumference of a circle, I'm not exactly sure what this is going to do. So the diameter.
I think my computer.
So here, this should be up here in the middle, bisecting the middle. I'll fix this later. So the circumference of a circle, you can also write it in terms of the radius, and the radius is half of the diameter, right? So the
Yeah.
circumference is either pi times the diameter, or it's 2 pi times the radius. So circumference is 2 pi r, or pi times the diameter. Depending on which you have, it's easy. It might be easier to do one or the other, but it's just that. Okay. So that's the end of that one. And there are others, but I think what I'll do is I'm going to stop there. And if you have any questions about earlier problem sets or anything, we can go back and look at those. Or
No, it's fine. I have a couple of them just completed. I just wanted to wait till I finished them all before I turned them in.
sure, no problem.
Just so I
Yeah.
can just go in and just type them all in.
Yeah, I think I've changed the required due date to the end of the quarter for everything. So it should be better that way. So give people more time.
Okay.
Yeah. Okay. So anyway, so yeah, well, thanks for showing up. That was, we'll so I'll get new problem sets out, because I know you want more problem sets to work on.
Kinda.
All right. So tomorrow we'll go through a couple more of these, just because I think it's a useful thing to do. I'm not sure why there's an algebra. I mean, there's a geometry section in a pre-algebra class, but that's not my